All right, so let's get started. So my name is Yu Fei Tao. I'm going to stay here for 1 year. I plan to do this service. I plan to do a series of seminars. And in these seminars, I'm going to pick a set of hot database problems, okay, hot database problems. And for each of these problems, I plan to have a systematic introduction to the theory underneath those problems, okay? So today we're going to start with this approximate nearest neighbor search problem. Okay, so I'm going to use ANN as a short form for approximate nearest neighbor. Okay, so let's first define the problem together. Okay, we'll be looking at a metric space. Okay, so we've got this metric space, and usually when you define metric space, you provide two things. Okay, so this M and D. I'm going to explain what this M and what this D are. Okay, so first of all, M is just a set, an arbitrary set. It can be finite, it can be infinite. It doesn't really matter. And you can, for example, you can imagine this M to be the D-dimensional space. Okay, so let's say two-dimensional space. By the way, two-dimensional space is a set. It's a set. It's an infinite set, right? It's a set of points. Okay, so that could be this M. So M is basically the domain, right? M could be three-dimensional, four-dimensional, et cetera, et cetera. However, it doesn't have to be Euclidean. You see what I'm saying? That's the beauty of this metric space. So for example, M could be the set of all possible strings, string text strings, or it could be the set of all possible images. Okay, so as you will see, we'll be looking at something mathematically beautiful that is able to tackle ANN search over all those domains. Okay, so this is something we will do in the first topic. Okay, now along with M, you also have a distance metric. Okay, a distance metric. So this distance metric essentially says that for any P and Q, so these are elements from the domain. Okay. By the way, I'm going to use this term point to refer to each element in the domain. But you have to bear in mind that they may not be really just a Euclidean point. All right. So this is just a definition. So if you have two elements, P and Q, namely points, okay, from M, and then this distance metric will give you something in the non-negative real domain. Okay, so intuitively, this is saying how far apart, okay, the distance between these two elements, P and Q. Okay, so for example, if you think about P and Q as two-dimensional points, and then you could define this distance metric just as the Euclidean distance, okay, L2 distance, right? Or you could define it as the L1 distance, or you could define it as the L infinity distance. It doesn't really matter, okay? If P and Q are strings, and you can define, for example, the distance to be the added distance between those two strings, okay? If P and Q are, I don't know, images, and then you take your favorite, similarity function, okay, to gauge how similar or how dissimilar, I don't know, those two images are, okay? So you can utilize a lot of different distance functions, okay? All right, well, if you call this pair M and D a metric space, then there must be some requirements, some assumptions that you have to fulfill, okay, regarding this distance function. So there would be three properties, three requirements. The first requirement is that if you measure the distance from the point to itself, and then it's always zero. Okay, so this is something that must be upheld, okay, in all these applications. And another assumption that you need, that we need, is the so-called commutativity. Okay, so this distance measurement will have to be symmetric in the sense that, distance PQ and distance QP, they ought to be the same. Okay, now finally, we also need the triangle inequality. Okay, so let's say you've got ABC here, and then, I should have this inequality for you to hold. Okay, so this is something very familiar to us, right? So you can imagine, feel free to fall back onto Euclidean space whenever necessary. Okay, all right. Okay, so that defines the metric space, all right? Now let's define what is nearest neighbor. And then I'm gonna go from nearest neighbor to approximate nearest neighbor, okay? So now let's think about a point in M. Okay, so that's a query point. Okay. Before that, I should have mentioned. So let's take one step back. So let's say you have a set of points. So this is a set of points from the domain. Okay. So I'm going to use this symbol n to represent the number of points in this set. So this will be our data set. Okay, this will be our input set. Okay. Now, if I have a query point, let's say Q. Now, this is an arbitrary element. Okay, arbitrary element in the domain, this M. And then I get to ask the question, right? Which point in this P has the smallest distance to Q, right? So this is something very intuitive. So I will define the nearest neighbor, okay, of Q as, D point in P closest to Q, okay? So this is the definition of nearest neighbor. And I'm sure this is something very intuitive, right? Something you already know, okay? Now, I'm going to move from here to this so-called the concept of one epsilon nearest neighbor of Q. Okay, what does that mean, right? So let's say P star, let's say that is the nearest neighbor of Q. Okay, so I have already defined this set here, right? So this big P. So this P star is well defined, right? Because this, as you can see, the definitions here, right? So this is something that I did something stupid, right? Okay, so how do I go back? How do I go back? All right, so that's interesting. Something I did not expect. Okay. Maybe I can shrink, and I cannot shrink, and that's interesting. I'm sorry, I should not have touched the screen. Okay, something. So what can I do here? What can I do? Let's see. What can I do? It's not changing. Okay. I'm sorry. What's that? What can I do? I didn't. No, I touched the screen. The resolution here remains the same. It's just that something. Okay, you know what? I can always reconnect, right? I will reconnect. Okay. Say I reconnect. Okay. Okay. All right. Now we're back. All right. So now we're back. Okay. So now if I say I don't want the exact nearest neighbor. Okay. So I would like to have a point in the data set. All right. A data point. Okay. The point will have to come from the data set P. However, this point is almost my nearest neighbor. So in that case, we are interested in some point. So a point such that it satisfies the condition that the distance between Q and P is no more than 1 plus epsilon times the distance from Q to its nearest neighbor. Okay, so in this case, P is defined to be a 1 plus epsilon nearest neighbor. Okay, good. Now, what is the problem? The problem is a data structure problem. Okay, so here we would like to build a data structure on P. In the database terminology, we would like to build an index. Okay, so we'd like to create an index on P. And then when I finish the construction of the index, okay, when the index is ready, I say, okay, now hit me with whatever query point you want. Okay, you give me a query point, and then I'll return to you a 1 plus epsilon approximate nearest neighbor. Okay, by the way, you could have multiple points that could be returned, all right, in which case you could give me an arbitrary one. Okay, when there are multiple points that could serve as the answer, feel free to give me any of those. Okay, all right, so I want to do this fast, okay, because one simple way to achieve the purpose is to simply scan all the points in the data set, right? So for every point, you spend constant time calculating the distance, from this point and the query, and then after n time, you will be able to solve any query, right? So this is the baseline, right? So you can create nothing. So basically, you'll be using n space because there are n points here, and you can get to answer any query in n time. Okay. So now the challenge is how to do this thing faster. Okay. So this is the goal. All right. So this is the goal. Well, you can imagine this problem. This is really, really a classic problem in computer science. And in recent years, the database community has picked up new interest in this problem. And one very important reason is because of this LLM. Now we can map a lot of things to vectors, right? So you can use BERT, for example, to map words or sentences to vectors. You can map images to vectors. You can map anything to vectors. And actually, those vectors, they have semantic meanings. Okay, so two vectors are close if they are semantically relevant. You see what I'm saying? All right. So LLM is really hot, and AI stuff is really hot. And in order to apply a lot of AI techniques, this is what you need, right? So I give you a query. Let's say I give you a sentence. I want you to find the image that's closest to my sentence, right? Like Michael Jordan playing basketball. So that's precisely ANN search, right? Okay. All right, so this is, on the other hand, a very difficult problem. In fact, one very tough competitor is exactly the so-called brute force scan or sequential scan. Okay, so this big O of n time is very difficult to beat. Okay, if you look online today, I would say there are at least several hundred papers using a technique that we are going to discuss. 100 papers, I mean, on different variants of this technique, right? So this technique is called proximity graph. Okay, so this has been adopted by industry. Okay, so this is not really just a random technique. This is a very, very important technique. Okay, so this is called proximity graph. So in the first topic of this seminar series, my objective is to discuss about this proximity graph. So let's discuss about this topic together. And my goal is to introduce to you the theory behind this PG, okay? And the theory is still under development as we speak, because this is such a new topic. So people do not really have thorough understanding about proximity graphs yet. And however, just as system people are developing more and more efficient proximity graphs in practice, theory people are also trying to catch up by providing the theoretical justification of a lot of phenomena that we are able to observe in practice. Okay, so let's define this proximity graph together. And after that, you will get a strong feeling why such kind of graphs have attracted so much attention from the industry. Okay, as you will see, once you are able to build this graph, the query algorithm is super simple. Okay, so I'm going to define a proximity graph. Okay, so I'm going to define it in a procedural manner. Okay, now let's say you have got a graph, and this is a directed graph. So you know, when we define the directed graph, I have to give you two things, right? So what is the set of vertices and what is the set of edges, right? So here, the set of vertices, very simple. The set of vertices is simply the set of points. Okay, in other words, for every point in the data set, it will also serve as a vertex, right? Okay, so that's it, right? But also, I have to define the edges. Okay, so I have to define the edges. In fact, this is a definition of proximity graph. And I would tell you, after you have given me a directed graph, satisfying this property, B, B, and P, right? I tell you whether or not your graph is a proximity graph, a 1 plus epsilon proximity graph. Okay, so as I said, this is going to be a procedural definition, okay? All right, so you have this graph, and I would see if it allows me to do the following nice thing. Okay, so you have this graph, and I would say, okay, I start from any vertex. When somebody gives me a query point, right? So you remember there's a Q in the beginning, right? I want to find a 1 plus epsilon ANN of this query point, right? So that's the setup, right? Okay, so your proximity, your G, if you call it a 1 plus epsilon proximity graph, okay, let's say 1 plus epsilon PG, okay? And then your graph should allow me to do something fancy, okay, something fancy. Now, what is this fancy thing? So I look at your graph, and I can start from an arbitrary vertex, okay, an arbitrary vertex, which I would call P start. Okay, P start. Okay, and then you will see I will be defining a greedy algorithm, a greedy process. Okay, so this greedy process takes two parameters, P start. This is really, really up to me. You see what I'm saying? You give me the second parameter, which is the query point. Okay. However, I get to choose whatever point, whatever vertex in the graph. So that's P star. Okay. And then, whatever happens next, you cannot control. Okay. So what I'm going to do is the following. Okay. So I look at this P star. Okay. And I look at the out neighbors of this P star. By the way, this G is a directed graph, right? Okay. So let's say I am the vertex, the P star, and I look at the out neighbors. Let's say I have 3 out neighbors, right? I look at all of them. So for each out neighbor, I calculate, let's say for this guy, P, I calculate the distance between P and Q, right? Of course, I also calculate the distance between myself, P star, and Q, right? And then I check whether P is better than me, right? Better when closer to the query point, right? Good. Now, that's what I do to P. But remember, I may have multiple out neighbors, right? And then I would do the same thing to every other out neighbor. Okay, for each one of them, I check whether that out neighbor is better, and then I will find the best out neighbor. You see what I mean? Like if I have, in this case, 3 out neighbors, and then I'll identify the out neighbor that's closest to the query point Q. Okay. Now I see. Well, let's say P is the best out neighbor. Okay, best out neighbor, and then I check whether this P is better than me. Okay, so just now I said I will identify the best out neighbor, but it's possible that none of my out neighbors is better than me. You see what I'm saying? Okay. Well, if none of them is better than me, and then the greedy algorithm stops right here. No more execution. Okay, so this will be the final answer. On the other hand, if the best out neighbor is better than me, and then I will be forced to jump from myself to that out neighbor. You see what I mean? Okay. By the way, if I do one jump, you can see that in terms of the distance to the query, it has decreased monotonically. It has strictly decreased because I don't even allow ties. You see what I'm saying? I say I jump from myself to an out neighbor if I see a strict improvement. If I don't see a strict improvement, no deal. And I'll be returning myself. The greedy algorithm is going to stop right here. I will jump to my neighbor only if my neighbor gives me a strict improvement. This strict improvement is very important because, as you will see, this is what the greedy algorithm relies on in order to guarantee termination. Okay. So that's one step, all right? And then what you can do is to perform the step repetitively, right? And then you hop on to your out neighbor. So now I become my out neighbor, right? And then I look at my out neighbors again, right? If I see a strict improvement, I jump again, I hop again. I keep doing it. As you can see, I cannot go on forever. Why? Because every time I jump, I require strict improvement. So the distance keeps decreasing, right? So in the worst case, you will terminate after n hops, right? It's not possible for you to go on forever. Okay, good. So that defines this greedy process. Okay, as I said, if you can call your graph a 1 plus epsilon PG, and then you must be able to allow me to do something fancy. You will have to guarantee that I do this. Now, remember, I have lots of freedom in doing it because I get to choose whatever vertex as the starting point. Okay, so I do this, and every single time, this greedy algorithm will have to return a legal answer. Okay, legal answer. So that will have to be a 1 plus epsilon ANN. Okay, if that is the case, that's the proximity graph. So as I said, this algorithm is super simple to implement, right? Super easy to implement, right? In system implementation, this is very, very important because you don't want to use a super complicated algorithm. You know, that's going to probably create a lot of issues in the development. But this algorithm is super simple. And furthermore, you can easily implement it no matter whether the data fits in the main memory or some of the data will have to be stored in the disk, right? Because all you need is to store the graph, and that's it, right? Okay, good. So if this is the case, and then we say that G is a 1 plus epsilon proximity graph, of this input set, as I said, right? So when do we get to say that G has this name? If the above greedy process always returns a legal answer. Okay, this will have to be true regardless of the choice of P star and Q. Okay, so this is very important. Okay, so this is proximity graph. Okay, good. Well, the first immediate question is, how do we find such a graph? Right? How do we find such a graph? Now, indeed, this is going to be the main target of our discussion. Okay, so we will understand, try to understand a part of the theory behind PGs. Okay, so one immediate question is, can we guarantee that such graphs even exist? Okay, is it possible to say that it always exists? Okay, it does. We are able to. It does always exist. So for example, one most trivial proximity graph would be the complete graph. You see what I'm saying? Like I'm a point and I have an edge to every other point, right? And if you are a point, you also have n-1 edges, right? So in that case, if you think about it, okay, you can try this greedy algorithm, right, on that complete graph and convince yourself that this is indeed satisfying the requirement. Right? Actually, even better, you can always find the exact nearest neighbor. Okay. So the complete graph, on the other hand, has a lot of edges, right? The number of edges is n squared. The industry hates n squared. Okay, so this is not something that's going to work, right? So a very natural question is, okay, how can we build a proximity graph that satisfies two requirements? First, it's provably small. Okay, it has edges far less than n squared. And the second requirement is provably fast. Okay, provably fast. Okay, all right. Now, these two questions are not easy to answer. It's going to take us, several seminars to fully understand it. So every week we have a small bite. Okay, so we're going to do things, in an hour, have a small bite, and we digest it. And next week we continue. Okay, all right, nice. All right, so now let's delve into the theory of proximity graphs. Okay, now you already know this is a fancy definition. Okay, this is a procedural definition. So next, I'm going to give you an equivalent definition. Now, this definition is this definition is more useful when you have to judge, when you have to check whether a particular graph is indeed a 1 plus epsilon PG. Okay, so this algorithm is good in the sense that it's very easy to understand, and also it tells you immediately the usefulness of PGs, right? Because you see the algorithm immediately, so you get convinced about its usefulness. However, the problem with this definition is that if I give you a G and I say check it, tell me and prove, okay, whether this is a proximity graph, and then you will say, that's pretty hard because all I have is this greedy algorithm, and I don't have anything mathematical, right? I don't have anything about the mathematical structure of such a graph, right? So ideally, we would like to have something that we can check, or we can try to prove that this graph indeed has this property, and this property is an if and only if property of being really a proximity graph. Okay. So next, I'm going to give you such a property. Okay, so this is going to be a very important property. Okay, so if you want to check whether a graph is a proximity graph, this is what you rely on. All right, so now let's say G is such a graph. Okay, as I said, the vertex set is always P, so I just use P directly. Okay, and you have the directed edges given. Okay, so now I'm going to give you an if and only if property. Okay, and if this graph satisfies the following property, it must be a proximity graph, and vice versa. Okay. All right, so this definition, this property is called 1 plus epsilon navigability. Okay, navigability. Okay. So let me tell you what is this navigability. So it says the following. Okay, the following will have to be true. Now this is going to be a strong condition. Okay, so it says for any p in the data set, okay, small p by the way, for any small p in the data set, and any query, okay, from the domain. Okay, the following will have to be true. Okay, so at least one of the following is true. Okay, so I will first give you the definition, and then I'll explain the intuition. Okay. So the first thing is either P is already a legal answer. Okay, so this is the first possibility. Intuitively, this means, okay, good. All right, so P, you have already found P. Okay, or if P is not a legal answer, P has an out neighbor, P out, that gives you a strict improvement. Okay, such that the distance between Q and P out is strictly less than the distance between Q and P. Okay, so this is what it means by 1 plus epsilon navigability. Okay, so let me explain to you, in layman's words, right? Essentially says if the graph that you give me is good, and then it needs to be good in the following sense. Okay, for any query, well, that's not surprising, right? Because you have to serve whatever queries I give you. So for any query, I should be able to see the following property. I should be able to see like, okay, I got a point here. I take any point, right? And then I ask the question, is this point already a legal answer? Okay, if so, you have already satisfied the first bullet. But if this point is not a legal answer, and then this point must have an out neighbor that gives me a strict improvement compared to the point itself. Okay. So if this is the case, and then you can imagine that the greedy algorithm is going to be able to continuously improve itself, right? If I start from this P, right? If I cannot terminate at this P, and then I will have to find something that's strictly better. And then the process can be repeated because now I jump over to that out neighbor. If that out neighbor is not something I can return, and then that out neighbor will give me something else, that will present a strict improvement, right? And then the process is going to repeat itself, right? So basically, this proves one direction of this if and only if, right? And the other direction is more involved, okay? And this is something I have already written down in the lecture notes, okay? Now, just in case you didn't know, I have already released the lecture notes for today's talk, okay? And I also plan to release the video, okay? Okay. All right. Now, this is something we will hold on to, okay? So this 1 plus epsilon navigability says, now this gives you a non-procedural definition of what is a 1 plus epsilon PG, okay? So now we have got two definitions, all right? So the second one is the one that we will rely on, okay? Good. All right, I still have 30 minutes today. Now, for the second part of the seminar, I'm going to introduce one proximity graph in the literature that has become famous since 2023 because in 2023 there was a NIPS paper by Indik, so there's MIT professor, right, and also his student. So there's this paper. So this paper examined all the proximity graphs that existed, at that time. And Indik is a theoretician, okay, and he looked at each one of those proximity graphs and he tried to understand whether any one of them, possessed theoretical guarantees. Okay, he looked at everything he was aware of, and then he identified this one, and he also proved that all the other proximity graphs did not carry theoretical guarantees. Okay, so what that means is if that graph has to return a legal answer, and then in the worst case, you will have to scan endpoints. Okay, so it does not really present an improvement over the brute force scan, right? Well, the method that I'm going to introduce next, and this method is called, by the way, disk ANN. And interestingly, disk ANN provides strong guarantees. Okay, so now this is something that is very good for education purposes. Okay, so we look at this and we understand, a lot of things behind proximity graphs. Okay. Now let me first tell you how this method, disk ANN, builds a graph. Okay, and then I'm going to prove that this is a proximity graph, and this is not trivial. All right, and then that will be everything I have for today. Okay. So this is an algorithm. All right, so this algorithm says you give me any set P, and then I can construct a graph. Okay, so let's see how this graph is constructed. Okay. Now, first of all, we will introduce some values, this alpha. So I will set this alpha to 4 over epsilon. By the way, what is epsilon? So remember, right? We want to do 1 plus epsilon ANN, right? So you can see this alpha is just some value, right? So for example, alpha could be like 1/2. Now in that case, epsilon could be 1/2. In that case, and alpha will be something like 9. Okay. Indeed, in practice, you can think about alpha as a something that's larger than 1. All right, so this is let's say 9. Okay, so in practice it would be like 10, 100, something like that. Good. All right, so I'm going to I'm going to explain how the graph is built. Okay. Well, let's say P is a point. Okay, so this is a vertex in the graph for sure. Okay, now in order to build the graph, I'm going to generate the out edges. Okay, out edges. I say out edges to remind you that this is a directed graph, right? Outgoing edges, right? Okay, good. So I'm going to determine the out edges in the following manner. Okay, so let's take it slow, right? So one step at a time. So first of all, I'm going to look at all the other points. So P is the input set, right? And this small p is the point I care about, so I take it out. Now for the remaining points, we want to sort them in ascending order of their distances to P. Okay, so sort, okay, according to distances to P. Okay, so now you can imagine you have a sorted list of size n-1. Okay, n-1. Good. So let's say L is the sorted list. Okay, good. Now what I'm going to do is I will look at every point in the sorted list in turn. Okay, so this is sorted list, as you can see, I call it L, right? So I will look at every point in L in turn. Okay, good. All right, so now let's say this is the next point, in the sorted list. You can imagine inductively, right? So let's say at some point, I come to this point, and this point, let's call it U. Okay. So for the next point on this L, you will see the processing of U, okay, this point here, is going to eliminate some of the points from this list. Okay. So it's not like, we will really create an edge to every single point on the list. Okay. Now, once again, what I said is that, after we have processed this point U, this list is going to be shorter. Okay. Some of the points might get discarded from the list. Okay. So once they disappear, they never come back. All right. So the processing of U potentially will shrink the list L. Okay. All right. So this is what's going to happen. Now, if this point U is the first point on the remaining list, okay, and then we create an out edge from P to U. Okay. So U is here, and then there is an edge from P to U. Okay, so I want you to think about this inductively, right? So if U is the first point on the list, and then yes, you definitely have an edge from P to U, but sort of that's sounds like a reasonable thing to do, right? Because U would be the closest point to P in that case, right? So you want to create an edge from P to that point, right? But inductively, let's say U is the first point on the remaining list. Okay, and the first thing you do is to create an out edge from P to U. So intuitively, U is good. Okay, so it's a very important point. Okay, we would like to keep it. All right, so that's the idea. And then you want to ask the next question, right? After you have already decided to keep this point U, hey, maybe you are able to discard some other points that are much less interesting because of U. You see what I'm saying? Okay, all right. Now, I'm going to tell you exactly which points to kick out of this list L. Okay. Well, think about some point like this. Okay. It's PUV. Okay. I put their positions like these because I want to get the impression, look, this V is so close to U compared to P. You see what I mean? Now, think about what's happening like this. Let's say P is in Singapore and U is New York. You see what I mean? Okay. And V is Boston. New York and Boston, right? So pretty close, right? And you have already got a direct flight to New York. You see what I'm saying?
would you also have another flight from Singapore to Boston, right? So that's the idea.
Okay.
The answer is no.
Okay.
However, that's a very intuitive, informal description, right? So formally, what is the criterion we use to forget about like V? Okay, so this is the following inequality. So discard, V from L if the following is true. All right, so the distance between U and V, is strictly less than 1 over alpha. The distance, I'm sorry, just D, okay? The distance between P and V, okay? So this inequality, now remember alpha is something like 9, right? 9. So essentially it says, okay, think about the right-hand side first. P is our current location, right? So Singapore, okay? So we know that we have decided to cap U, right? So that's the premise, that's the condition, right? So we know that we have a shortcut to U immediately, okay, intuitively. Well, if that is the case, and then this U, the presence of this U, if we pay constant time, right, performing this jump, and then this hop will allow us to reduce our distance to our destination by at least a factor of alpha. You see what I'm saying? Okay, so that's the intuition behind this, right? So it makes sense. So if you do this, you can imagine that since we have decided to cap U, and a lot of guys, those guys are farther away from P, right? And many of those guys could have been shielded by U. You see what I mean? Because of U is there, it has blocked the necessity of keeping those guys, right? So that already gives you the feeling, hey, yeah, we might be able to remove a lot of points like this, right? Okay. So that is the processing of this point U. Okay, that is the processing of this point U. So after this, you can imagine that the list has shrunk. Okay, the list has shrunk, right? And then you repeat this. Okay, you repeat this. All right, so the next point, you decide to keep, but then keeping that point will allow you to shrink the list further. Okay. So in the end, when L becomes empty, you have determined all the out neighbors. All right, so that's how the disk ANN algorithm works. So now you have got a graph. So let's say this graph is GDA, right? Disk ANN. Okay. So we will discuss this GDA. Okay, we'll use this GDA as an example to understand a lot of things about PGs. Okay. So the first thing that comes to our mind is, why is this a 1 plus epsilon PG? You see what I'm saying? Okay, so this is only a graph that is constructed by disk ANN, but it doesn't mean that we have to accept it. You see what I'm saying? Okay, in order to accept this, we have to convince ourselves that this is a correct graph. If it's not even a correct graph, and then we don't want to spend time talking about it. So, because we're talking about theoretical guarantees, right? So the first thing we have to convince ourselves is to prove that it is 1 plus epsilon navigable. Okay, now still remember the definition of navigability, right? So it says for any query Q and for any data point P, something very, very stringent will have to hold. It says either this point is a legal answer, or one of the out neighbors can give you strict improvement. Okay, if so, and then we are convinced this is a 1 plus epsilon PG because navigability is if and only if with PG. Okay, good. All right, now I'm going to prove this, and this is going to be the content of the last 15 minutes. So as you can see, this is how the graph is constructed. And let's summarize the key property from this algorithm. And this is the so-called shortcut property. Okay. So the shortcut property says for n, you fix any point P. Okay. And then the following must be true. Holds for any V other than small p itself. Okay, p is a data point, by the way. So the following holds. So either, PV is an edge. So this means either P is directly connected to B. Okay. Or there exists an out neighbor Okay, so there exists an out neighbor of P, and this out neighbor serves as the shortcut, okay, such that the distance from P to B is, okay, so let me write it in from the perspective of P out. This will have to be less than 1 over alpha times the distance from P to B. Okay, so let me make sense of this for you. Okay, so it says, you look at any vertex basically, and you look at any other vertex V. Okay, the following must be true. Either V is an out neighbor of P, so I already have a flight from P to V. But if I don't, then I definitely have an out neighbor. I already have a flight that can bring me much, much closer to the destination. Okay, so if you look at the right-hand side, this PV is my current distance from P to V. And I know V is something that I do not have a direct flight to. So I rely on my out neighbors, right? And indeed, I can find an out neighbor. It's so good that I can go to my out neighbor, with one edge, and then from that out neighbor to B, the remaining distance is like 1 over alpha of the original distance, right? So that's why you can think about this edge from P to P out. So that would be a shortcut. You see what I'm saying? So that's the shortcut property. Okay. So I will not explain in detail why this shortcut property holds, except to say that this is pretty much essentially what the algorithm is doing. Okay. All right. So in the lecture notes, I said this is a brain teaser. Okay, so you look at the algorithm, and I want you to prove this for yourself. And if you are able to do this, that will enhance your understanding of this algorithm, right? But this is really, really not supposed to be difficult. Okay. All right, now let's prove that this ANN graph is a good graph. Okay, so we want to prove that the disk ANN graph is navigable. All right, so this is our main lemma today, is 1 plus epsilon navigable. Okay, so let's prove it. Okay. All right, now in order to prove this, I will have to allow you to choose any Q and any P. Okay, choose any Q from the domain and choose any P from the data set. Now let's recall the definition of 1 plus epsilon navigable. It says we have to prove the following, right? Either P is a 1 plus epsilon ANN of Q, or what? Or there exists an out neighbor P out of P, okay? Such that the distance between P out and Q strictly improves my distance. Okay, so this is the definition of 1 plus epsilon navigable, right? So we want to prove that this is true. Okay, want to prove this is true. All right, now you can see if P is already a 1 plus epsilon ANN of Q, there's nothing to prove, right? Because it trivially already satisfies the condition. So now in our subsequent discussion, we'll assume it suffices to consider actually, okay? Assume that P is not a 1 plus epsilon ANN of Q. Good. Well, if that is the case, let's identify the nearest neighbor, the exact nearest neighbor. Let's say P star, let's define it as the nearest neighbor of Q. Okay. So this essentially says that if you look at the distance between P and Q, this will have to be at least 1 plus epsilon, actually strictly larger, strictly larger than 1 plus epsilon, the distance between P star and Q. Okay, so that's the definition of 1 plus epsilon nearest neighbor. Right? So this will have to hold. Okay, good. Now this is something we'll utilize later. Okay, good. Now we ask the question, do we have an edge from P to P star? Okay. Well, if we indeed have, such an edge, and then we're done, because this will be our guy. You see what I mean? Because we want to find our neighbor that can give us strict improvement, right? But P star, well, that's the best guy we could ever get, right? So of course that would be strict improvement because I know that I am not the nearest neighbor, right? Actually, not even close. I am strictly larger than this 1 plus epsilon of the nearest distance, right? Times the signal. Okay. So in this case, if so, yes, and then we are done. Okay. Now in terms of logic, the remaining case is to consider how about no? Okay, so P star is not an out neighbor of P. Okay, all right, good. Well, if this is the case, we'll utilize the shortcut property. Okay, we'll utilize the shortcut property. So I'm going to continue here. Okay, so I want to give you a picture to visualize what's happening here. So let's say P, so that's our current hop, right? So we already know that P star is not an out neighbor, right? So the shortcut property essentially says that there must be some out neighbor of P out, and this P out will bring us much closer to P star, right? But I also want you to imagine where this query can possibly be. You see what I'm saying? Because P star is supposed to be the nearest neighbor of Q, right? So Q will have to be somewhere around P star. You see what I'm saying? Okay. So that's going to give you a big picture of what is going on intuitively. You can see our ultimate goal is to prove that this P out gives us a strict improvement compared to P, right? And this picture will allow you to believe that, this could be true, okay? Because, what I said about the relationships of all these guys, right? Okay, good. Now, finally, we will turn this intuition into a formal proof. Indeed, this P out is our guy. Okay, so once again, what is P out? Now, P out is the point promised by the shortcut property. Okay. Now, what is the shortcut property? Well, okay, let's zoom into here. So it says, if you look at the distance from P out to P star, what do we know? This will have to be smaller than 1 over alpha of what? Okay, so this is the distance from the previous hop, right? But remember, this is from P to P star. Okay, good. All right, now with this inequality, let's do some derivation. Okay, let's do some derivation. So I'm going to prove P out. I'm going to reason with this P out and Q. And my goal, now I emphasize this is my goal. I don't have this, okay? But I would like to prove that this P out is a strict improvement of this PQ, right? If so, and then, it satisfies the 1 plus epsilon navigability, and our job is done here. So this is, as you can see, I put a red circle here to remind myself this is not something we already have. That's actually the goal, right? Okay. All right, so let's do it. Now I'm going to start with a string of derivation. This is actually already in the lecture notes. So I apply triangle inequality here. Okay, so P out and P star. Oh, I want to see the picture here. Okay, you can see the picture here. So I apply inequality. So I get one step. As you can see, I get one step here. Okay, so for this P out and P star, right? So P out and P star, right? So I want to relate this to P and P star. You see what I'm saying? Okay, so I will apply the shortcut property here. Okay, so this is strictly less than P and P star over alpha plus, you know, I'm just copying this term over. Good. All right. So eventually I want P LQ and PQ remaining, right? I don't really want P star in the picture eventually, right? Because that's what I want to prove eventually, right? So I try to get rid of it by using triangle inequality again, right? Okay, so now I know that this is less than or equal to dpq. Now I use q as the bridge, okay, to do so, to get rid of this p star, and then d q p star. Okay. All right. So now I have this. So the good news is q is now in the picture, but I still have this p star, right? I will have to do something to get rid of that as well. Okay. There's one more term in the end, right? So this term is taken directly from here. Okay. Good. All right. So the good news is now q is entering the picture, and that seems to be what we want eventually. But still, we got this p star, right? All right, but the thing is, P star, you know, this Q P star distance has some relationship with this PQ, right? Don't forget this P is not a 1 plus epsilon A and N, right? So it means there must be some relationship between these two guys. Actually, the relationship is right here. So what you want to do is you want to leverage that relationship. You know what? I'm going to rearrange the terms a little bit so that you can see better. Okay, so this TQP star, and then 1 plus 1 over alpha, right? So this is, you know, just some simplification. Okay, and now I'm going to replace this term with dpq, right? And then I will be relaxing, right? So I'll be using this inequality to relax everything. So now this is dpq over alpha plus dpq over 1 plus epsilon, and then you get 1 plus 1 over alpha, right? So the remaining thing, the remaining derivation is pretty straightforward. Okay, so I take out this dpq. As you can see, finally, I have achieved my purpose. I have p, q, and p out, and nothing else, right? P out here. Okay, and then I have 1 over alpha plus 1 over 1 plus epsilon here, and then there's another term here. Okay, wow, such a complicated term. Still remember what is alpha? Okay, so so I chose this alpha very strategically. Okay, now you understand why I choose the alpha, you know, that way, right? So remember, alpha is 1 plus 4 over epsilon. It's not really the unique choice that will make everything work. Okay, so in fact, you can set alpha to be anything larger than this. Okay, so that will also work. Okay, but as you can see, this 1 over you know, this epsilon will have to be in the denominator, right? So the smaller epsilon, the better precision, but larger the alpha. So you can do the math. Okay, so this is something very elementary. So you can verify that when alpha is this value and then this guy is less than 1. Okay, so now we can happily declare that this is less than dpq, and that achieves our purpose. Okay. All right, so that's everything I have for today. Hopefully I'll see you next week. Bye-bye.